It's a real pleasure to be here. In fact, this is only the second time I've got out of the airport in Denver. The first time was actually back in 1981 when I was working for a mining company. And I was here, it was a Canadian mining company, and they had an office, an exploration office here in Denver. And I flew in here. It was around Thanksgiving weekend. There was snow out there, and believe it or not, I met up with one of the US Geological Survey geologists that was on my thesis committee, my Ph.D. thesis committee, that evening. And but I had the joy of seeing some of the countryside around here and going and visit some of the uranium properties that they were looking at for exploration purposes and what has happened here in the past in mining, uranium mining. But it's a real pleasure to be with you here again tonight. And we've got two things to talk about. Now, for some of you who have been at the rate conferences, some of this will be revision. Certainly there'll be more detail than what was had at the rate conferences. If you've read the rate books, well, this is also revision, but it's nice to be revision, to remind you of what the research was all about. My second talk is not only revision, but it's also an update on some of the later work that I've been doing, because I'm continuing to do this kind of research. And in fact, sitting on my desk at the moment is a meteorite that we're going to actually use for do radioactive dating on, because most people don't realise that the age of the Earth is not based on Earth rocks. It's actually based on meteorites. And so it's important that we take that research, these research results I'm going to share with you tonight. If we want to really challenge this icon of evolution, then it's important to also challenge the radioactive dating of meteorites. Now, I begin by talking about the creation of the Earth and the universe and its age. For many people, the Earth and the universe have an appearance of age. They look old. But why do they look old? It's because if you use the wrong assumptions to interpret the evidence, it can lead to the wrong conclusion. You see, people are looking at present-day rates of geological and other processes, nuclear processes, radioactive decay. They're looking at redshifts and the speed of light in the present, and they're making assumptions about those processes in the past. Now, if you make the wrong assumptions based on present-day observations, you could lead you to the wrong conclusions. Whereas if we start with the scriptures, we're given a different history for the age of the Earth and the universe. So the Earth only looks old because of the assumptions that are used to interpret what we see and measure. So, as I said before, it is assumed that geological processes have always occurred at today's rates. Now, you all know that rivers carry sand and mud very slowly. I mean, even the mighty Colorado River doesn't carry a lot of sand and mud down, apart from the dams, but even before the dams were there, a lot of sand and mud didn't get down to the delta. And when you look at some of the rock layers in the walls of the Grand Canyon, if you assume that the sand and mud carried by the Colorado River formed those rock layers, those sorts of rivers, well, of course it would take millions of years. That's why it's so logical to many people who think that way. But when you take into account what the Bible says, of course, then you get a different picture of looking at that evidence when you in terms of a global flood. But that's another story. We want to look at the claims that you can make derive absolute ages for the rocks and for the Earth. And that has been determined by these radioactive or radioisotope dating methods. And so let me explain it to you, because we've got a few young people here tonight, so I don't want them to fall asleep too soon by getting too technical. So if you know all this, that's all right. You can just have a rest while we explain this. A parent atom decays, changes into a daughter atom, and the daughter atom is of a different chemical element. Okay? That's what radioactive decay is. A parent atom, one atom, changing into another atom, an atom of another element. And so This process is similar to the old-fashioned hourglass. Up the top we start with the parent atoms, and as they fall they change into daughter atoms. Okay? Keep that image in mind and it helps you to understand this method.
So like uranium changing into lead.
Correct. So uranium, you can imagine uranium atoms in the top, the sand grains at the top. As they fall, the falling is equivalent to radioactive decay, and when they get to the bottom they're now lead atoms. Okay? So it's quite obvious. How do you tell the time with an instrument like this? Well, if you know how fast the sand grains fall, and you start with none at the top, and you read on the label that this is a 5-minute clock, okay? When half the atoms are up the top and half the atoms are down the bottom, how long has the clock been ticking? 2.5 minutes, okay? And the rate of the falling is equivalent to radioactive decay. But you're making assumptions. What if you come into a room where you weren't there when someone started the clock? Okay? How do you know that the clock started with all the atoms up the top, all the sand grains up the top? What if someone turned it over and it was halfway through, a split second before you walked into the room? You understand what I'm saying? You've got to assume, you normally would assume when you look at that it started with all the atoms were originally up the top and there were none in the rock down below. So that's what the geologist assumes. He assumes that in the rock you started with potassium and no argon, the daughter. So they measure the amount of potassium in the rock today, the amount of argon in the rock today. They know from present measurements how long it takes from potassium to decay or fall to argon. They assume that that's been the rate of that process in the past, and so they calculate how much time it took for the argon you measure in the rock to have come from potassium. And so you're obviously going to be making assumptions. These are the different methods, the 4 major methods. Uranium decaying to lead, potassium decaying to argon. Now we've already mentioned those two. Then we've got rubidium decays to strontium, and one that you may not have heard of, samarium, decays to neodymium. Samarium and neodymium are what we call rare earth elements. They're very rare. They're not commonly found, but we find them in many rocks in very minute quantities, parts per billion, and that's sufficient for the geologist to do the measurements. Now what happens is a rock is chemically analysed for these atoms or isotopes. And so there's no issue about this, there's no question about the quality of the analyses. I mean, you wouldn't believe the laboratories, the monies that are spent on these laboratories. The equipment is first class. If you want to set up a radioactive dating laboratory, you wouldn't get change for a few $1 million. And the work that is done is top class. So it's not an issue that there's any fault with the actual analyses. They're high quality chemical analyses. The real issue is that the numbers, the analyses have to be interpreted to calculate an age. And that's where the geologists have to make some assumptions. They have to assume that all the daughter was derived by radioactive decay of the parent since the rock formed. In other words, all the sand at the bottom has come from sand falling from the top. That's as simple as that, just using the same analogy. So they have to assume that all the argon they measure in the rock has been produced by radioactive decay of potassium since the rock formed. That makes sense, doesn't it? Because then they do that back calculation that we referred to before. But we also have to assume, the geologist also has to assume that no other process has affected the parent or daughter atoms since the rock formed. What do I mean by that? Well, think of that hourglass analogy. the egg timer, the 5-minute clock, the sand grains falling from the top to the bottom. What if you weren't looking, you set it up, started the process, and you left the room, you left the kitchen or left the room, while you weren't looking, you were gone, someone sneaked in, lift up the lid and put some more sand grains in. So when you come back and read the clock, it's grossly in error because some other process has affected the quantities of the sand grains. Well, it's the same. Can you imagine rocks sitting in the ground for millions of years without rainwater and groundwater seeping through them, or hot volcanic waters and not dissolving some or adding some atoms? No. There's no way, because the geologists haven't been there over millions of years to make sure that there hasn't been any contamination or something like that happen. In fact, were the geologists there when the rock formed anyway to see whether there was only parent atoms in the rock? No, they weren't. So it's only an assumption that they make. Notice it's not an observation, it's an assumption. And then the third assumption is that the rate of radioactive decay has always remained constant at the rates we measure today. So in other words, the sand grains have always fallen at the same rate. Now, all those three assumptions have to be made so that you then can calculate how long it has taken for the measured amount of the daughter atom to accumulate from radioactive decay of the parent. So you take the chemical analysis and you do the calculation, and that calculation gives you the age of the rock. Okay? So the issue is, it's not the chemical analyses that are faulty, it's the assumptions. Because each of those three assumptions cannot be proven, they're taken by faith. And interestingly, we can show that there are problems with each of those assumptions, as we'll do so in a minute. So just keep in mind this process. It's quite simple. A parent atom decays to a daughter atom, and you have to make those three assumptions. So there are two types. This is just an aside for those with a bit more technical bent. There are two types of ways of calculating radioactive dates. Okay, radioisotope dates. There are what we call model ages or single sample ages. So for example, we get a sample of a basalt from a lava flow and we measure the potassium and argon in it, and with that one sample we can calculate a potassium argon model age, a single sample age. So these model ages require a knowledge of the initial isotope concentrations. That is, we have to know whether there was any argon in the rock to begin with. We have to assume that there was none, and the calculation of the age is based on that assumption. If all the daughter was not derived by radioactive decay from the parent, then the model age will be wrong. The model age will be wrong. The other type of radioisotope age is what we call the Isochron Age, and it's calculated from 4 or more samples collected from the same rock unit. And because it involves more than one sample, 4 or more at the very least, it's regarded as more reliable. Because what if one sample was contaminated? Well, it won't plot where it's supposed to on the graph that I'll show you in a minute. So you can actually tell whether any of your samples are contaminated. And so that's why the geological community regards isochron dating as far more reliable. In fact, they do not require any knowledge of the initial concentrations of the daughter isotopes. Okay, you don't have to assume all the daughter was derived by radioactive decay since the rock formed. In other words, you rule out, you don't have to worry about that first assumption. But you're still assuming that there's been no contamination. You're still assuming that no other processes have perturbed the system, and you're still assuming that the decay rates have been constant. So this diagram is a little bit complicated, but let me just run through it for you. You start at the top, and what you do is you measure how much daughter and how much parent is in the rock. Now see, you might have this one basalt lava flow, okay? And you get 4 or 5 samples from it. Now, these samples, because of the random distribution of atoms, and remember, rubidium is a trace element. So in one sample you might have 100 parts per million, in another sample you might only have 5 parts per million. But that's good for this method because 100 parts per million of rubidium, or say 1% of rubidium, will produce more strontium than 0.1% of rubidium. Okay, it'll produce less strontium. And so what happens is when you plot the parent on the horizontal versus the daughter on the vertical, you actually get the data points spread out on that graph. And you want them spread out because what you're doing is you're trying to fit a line through those data points, the line of best fit. And the more spread out they are, the better, because you'll have, as the statisticians will tell you, you'll get better fit statistics to your line of best fit. And I can see a few people nodding there because you're obviously mathematicians or done mathematicians in your technical work. So how does this give us an age? Well, go to the middle graph. Okay, when the rock formed, different samples from this lava flow have different amounts of rubidium in them, but they all have the same, the theory says they all have the same strontium starting composition. Okay? And so with time, so they plot as a horizontal line. Different amounts of rubidium as you go from left to right, greater amount of parent as you go from left to right, but the same amount of strontium. Okay, now as the clock ticks away, the sample with the greatest amount of rubidium is going to produce the greater amount of strontium. Less rubidium, less strontium. So that line actually tilts up, it pivots on the zero, from that zero point, okay? From the starting point, it actually pivots. And so the older the rock, the steeper the slope of that line. And that line is called the isochron, which means same age. It connects all those rocks, those samples, because it's from the one lava flow which erupted at the same time from a volcano. Okay, so the age of the rock should all be the same, but these plot at different points, and yet a line fits through them. The slope of that line, which is called the isochron line, actually is the age of the rock. So the steeper the slope, the older the rock. Zero age, horizontal, no slope. And so that's what we mean by an isochron. Okay, now for those of you who that was too technical for, okay, that's fine. Now you can switch back on again and we'll get back to something a little bit more simple. But I wanted to explain that for those of you who are more technically minded, because when we did this work, we chose to usually use the superior isochron method, and instead of using 4 or 5 samples, we went for overkill. And the reason why we went for overkill in using more samples than geologists would normally use is we wanted to make the point. In other words, we want our results to stick and not be challenged. So how reliable is these radioisotope dating methods? Well, let's remember assumption number 1, all the daughter atoms were derived from the parent atoms by radioactive decay. Assumption number 2, no other process has affected the parent-daughter relationship through time apart from radioactive decay. And number 3, the rate of decay has been constant. Okay, let's examine each of these 3 assumptions. Let's go to the Grand Canyon. Why not? The Grand Canyon is one of the best known places. It's in every geology textbook. It's in every tourist brochure, every tourist flyer. And there's some lava flows there in the western Grand Canyon that are so recent, you can see the craters still, the volcanic cones still on the north rim of the Grand Canyon, and the lava's trickled down the walls of the Grand Canyon after the Colorado River had carved out the canyon. And you can see some of these, see this cone there, and you can see some of the lavas pinned to the wall, like this one here. You can actually see where it flowed from the rim right down to the river. Some of these lava flows actually blocked the Colorado River and dammed it up temporarily before the water burst through and eroded out the basalt. And some of these lava flows actually flowed down the Colorado River. So how old are these lava flows in the Grand Canyon? They're so recent, by the way, there's some evidence that the more recent eruptions may have even been witnessed by the Native Americans. So they give potassium argon single sample model ages from 443,000 years all the way up to just over 1 million years. Okay, that's comparing two rock samples. We also extracted a mineral, the green mineral olivine, from which we get our gem mineral called Peridot. Some of you might have heard of Peridot. It's a gem variety of olivine. From these same two rock samples that give potassium argon ages, the whole rock gives an age of 443,000 years. Whole rocks give that age and 1.16 million years. We get potassium argon ages on the olivine from that basalt of over 20 million years and over 46.5 million years. That's minerals from the same rock samples. So why is it that you get these gross ages? By the way, the rubidium strontium isochron age is 1143 million years. Notice that? Over 1 billion years.
Haven't they taken samples from the lava flows in Hawaii and some of the pyroclastic material from Mount St. Helens and sent it for testing?
Yeah, we'll talk about Mount St. Helens in a minute, yes. And the lead, which is there's two uranium types of uranium atoms that produce two types of lead atoms, and you can compare them. The lead isochron age was over 2.6 billion years. And these are lava flows that are relatively young, younger than the Colorado River itself in the Grand Canyon. Interestingly, as we'll see in a moment, and we'll talk more about this in a moment, there's lava flows also, ancient lava flows down the bottom of the Grand Canyon, the Cardenas basalts. And I'll show you the dating of those in a moment, but the same rubidium strontium isochron dating method gives an age of 1111 million years. That's 1,111 million years using the rubidium strontium dating method. Notice that these young lava flows at the top of the Grand Canyon that are so recent, they block the Colorado River after the Grand Canyon was carved out, given exactly the same rubidium strontium age. Notice that? Exactly the same rubidium strontium age. What's going on here? Well, in the case of the potassium argon, the problem is that most of the argon didn't come from potassium decay. The reason why you get olivine that gives an age of 20 million years is because there is extra argon in the volcano, in the volcanic gases. Where did the basalt come from, by the way? Most people don't realise that basalts come from the Earth's mantle, not from the crust, the skin on the Earth's surface. Both of these basalts come from the same area of the Earth's mantle. So, the rubidium strontium results have nothing to do with the age of the rock, but they have everything to do with the chemistry of the source area from which these lavas came inside the Earth. So this is inherited. Just like the argon is inherited in the volcano, so is the rubidium strontium inherited from inside the Earth. It's not to do with millions of years of age. The recent basalt inherited its old quote-unquote age from its source inside the Earth. We said we'd talk about Mount St Helens, and sure enough, we will. You're all familiar with Mount St Helens. In 1980 it erupted, and you can see inside the crater it built a new lava dome. And my colleague Steve Austin, this is his work, he went up in 1986 to collect a sample from that a crack in that lava dome where new lava had been witnessed to intrude and cool in 1984. So this was only a very young rock, 2 years old. It was only 2 years old when it cooled in 1986. When he collected the sample in 1996, it was only 10 years old. Okay, and there's the lava dome up close. So this was formed in 1986 in that new lava dome, and he collected the sample and sent it to the lab in 1996. So it's only 10 years old by eyewitness testimony. Okay, so it gave potassium argon single ages for the whole rock crushed 0.35 million years, that is 350,000 years. He then separated the individual minerals. One mineral called feldspar gave a similar age, another mineral called amphibole gave an age of nearly 1 million years, another mineral called pyroxene gave an age of 1.7 million years, and then a hand-picked concentrate of that pyroxene mineral gave an age of 2.8 million years for a rock that was only 10 years old. In other words, the rock contained inherited argon. Argon is a gas, and it's part of the volcanic gases that come up with the lava in the volcano. So again, the rock inherited the excess daughter atoms, and it makes it look artificially old. Now this begs the question, when we can eyewitness the true age of this rock and we find that the argon in it was inherited and to give a false age, how do we know that that's not the same as when we get an old lava flow and test it and it gives an old age? Could it be that most of the daughter atoms in it were also inherited from its original source? The answer is yes. There's no reason why that might not have been the case. In fact, and this table appears in these have all come out of the scientific literature. This table appears in the first rate book that was produced in 2000. This is all documented from the secular scientific literature, where they have taken, and you can see in answer to your question, some of those are Hawaiian lava flows of different known ages. For example, one there, the eruption was in 1800 and 1801, and using potassium argon it gave an age of up to almost 23 million years. So this is well documented in the literature that you actually can inherit more daughter atoms than what was produced by radioactive decay. Now, one thing that you will not be told is that there's lots of islands out there on the ocean floor. You can see some of the names there, the Hawaiian Islands, of course, the Canary Islands, the Azores, Reunion Island, and all of these got active volcanoes on them. We call them ocean islands, and they're made up of basalts. When we sample those basalts and date them using the lead-lead dating technique, that is comparing the lead from one uranium atom, type of uranium, uranium-238,